Hello and welcome to day 7 of our Unit 11 notes. Today we're going to talk about curve fitting or regression without a calculator. Ultimately, what we're going to be doing is getting information from certain situations that have trig-related applications, or taking trig-related applications and pulling some information from them to then come up with an equation. So just some vocabulary that you guys need to be aware of. First is amplitude. So as we know, our amplitude is our distance from the midline. So this is your amount above or below the midline. I tend to think about it as above the midline just because then it's like in the positive direction, but ultimately it's either. So you could use your amplitude and do whatever the maximum is minus D, which is representing our midline. So keep in mind down here, D is the midline. B, so our frequency is the number of full curves you'll see in 2 pi radians. So our frequency can be computed by doing 2 pi divided by the period. Now this is because we know from earlier in this unit, period is 2 pi divided by the frequency. So if you were to cross multiply, it would be B times the period equals 2 pi. Solving for B, you would divide by the period. So that's where this guy comes from. So we haven't used that a ton up until this point, but that will be useful for what we do today. Any sort of phase shift, left or right, we'll be aware of. It honestly doesn't come up a ton in our application problems, but we do know how to deal with phase shifts. Midline or vertical shift, that's that horizontal midline of your curve that the graph oscillates above and below. So I tend to think our midline is just right in the middle, so that means it would be the average of the maximum and minimum. So that's why it says max plus min divided by 2. So I'll put average of max and min. All right, our period is how long it takes on the x-axis to see one full curve. So as I said up above, and we know this from days prior, period equals to 2 pi divided by the frequency. So again, frequency we know is this B value. And then lastly, your maximum can be computed by doing the midline plus the amplitude or the midline minus the amplitude. And that is all the vocab that we've discussed over the last several days, and we're going to refer to that today. So our first problem is about hyperventilation. So during hyperventilation, which is rapid and shallow breathing, the volume of air in a person's lungs at a given time t is modeled by the following function, V of t equals 18 cos of 10t plus 30. Where V is the volume in milliliters and T is the time in seconds from the beginning of the attack of hyperventilation. What is the maximum? What is the minimum? So again, maximum, minimum is when we take the midline, which is why you guys are seeing this 30, and I add or subtract the amplitude. So amplitude would be 18 in each of those cases. So 30 plus 18 would be 48, 30 minus 18 is 12, and that's your max and min. And we discussed coming up with maxes and mins earlier in this unit when we asked what the new range of functions would be. So this cosine graph has a range of 12 to 48. All right, our next problem here. Ferris wheel at Landmark Navy Pier in Chicago takes 7 minutes to take one full rotation. The height h in feet above the ground of one of the 6-person cars can be modeled by the following function, where t is time in minutes. Using h of t for one full rotation, this car's minimum height in feet is. So what I want to point out here is they gave you a ton of information and honestly a crazy looking graph, but ultimately what it comes down to is it just wants to know the minimum height. So height is your y value, and we know that to figure out a minimum, we're going to take the midline, which is where this 80 is coming from, and we're going to subtract the amplitude, which is 70, and that's where we're getting a height of 10 from. Now, if I wanted a maximum just for fun here, my maximum would be, again, the midline plus the amplitude, which is where 150 is actually one of the options. So 150 would be your maximum, 70 is actually the amplitude. And 0 is actually really nothing helpful in this problem, so that one's just a throwaway answer. All right, question 3. The graph below shows the number of daylight hours for each day of the year in Fairbanks, Alaska as a function of the day number of the year. So for example, January 1st is day 1, January 2nd is day 2, and so on and so forth. What's the midline? So what you guys are seeing is a bunch of data pots, or data points, I think is the word I'm looking for there. So it kind of looks like a cosine curve, okay? Because it kind of looks like, actually a negative cosine curve, because as we have jokingly said, it kind of looks like a ghost. Boo. Okay, so this is your cosine curve. So if we're approximating here what the midline is, let's say that using our scale, we'll say that our lowest value maybe is like a 3 and our highest value is maybe a 21. Okay, approximating here. Midline is again the average of the max and min, so that's why we do max plus min divided by 2. Plug in 21 for your max, 3 for your min, and divide by 2. And then you get 24 divided by 2, which is 12. So keep in mind that's going to be your D value in this. Amplitude is when we do the maximum minus the midline, so that's why we're taking 21. Again, this is your maximum, minus the midline, that's 9. Or, think about it this way, if your midline is 12, which we have drawn in here, think, what's the difference? To get from 9 to 21, that would be, or sorry, from 12 to 21, that would be 9 units. All right, now, what is the period and the frequency? So they're talking about this over the course of a year, right? So the graph shows the number of daylight hours each day of the year, and we'll go by the basic 365 days. We'll pretend this isn't a leap year. So if we're going 365 days in a year, so say like that's like there, okay? If the period is 365 days, frequency, which is the B value, is equal to 2 pi divided by the period. So this, if I peek back up here, is this relationship. Frequency equals 2 pi divided by the period. Okay, so frequency equals 2 pi divided by the period. Then I'm plugging in 365 for the period, and that's where you're getting this from. 2 pi over 365. Now, putting it all together into a cosine curve, which makes sense because it looks like a cosine curve, using A, B, and D. A is your amplitude, B is your frequency, D is your midline. I'm going to plug in the 9 for the amplitude, but notice how there's a negative there because it's a negative cosine curve. It's starting below the midline. The frequency, this 2 pi over 365, is going in for B. And then the midline, which I had figured out up here for 12, goes right there. So my function is negative 9 cosine of 2 pi over 365x plus 12. And that's the equation that best fits our picture here. Now, according to the graph, around which day of the year did the first day of the year with 17.5 hours of daylight occur? When does your function part A agree with your estimation? Oops, my thing jumped. Okay, so I want to find when there will be 17.5 hours of daylight. So 17.5, if I had to approximate, is like right in there. I'll say that's about where 17.5 would be, which is where we're saying approximately like 120 some days maybe is my approximation for when that first hits. Let's actually find where that is based on our model. Now, if we plug 17.5 in for our hours, our y, I'm looking to solve for x here. Now, something to note is that this 2 pi over 365, that is a frequency in terms of radians. So in order to solve for x, the first thing I would do is try to isolate this part of the equation. So that's why you're seeing me actually subtract 12. And that's where this 5.5 is coming from. And then I'm actually dividing by -9. Okay, because again, I'm trying to isolate this cosine of 2 pi over 365. Now, on the left side of this equation now, I have -5.5 divided by 9, because that's from that right there. Now, this, I'm going to convert to degrees because my calculator is in degree mode. Okay, now we know that pi is equal to 180 degrees. So if I do 2 times 180 divided by 365, that's where this 0.986 number is coming from. Okay, so again, this is all because pi radians equals 180 degrees, and your calculator is in degree mode. In order to solve for x, we're going to have to undo x by using our inverse. So here I go on my calculator. So to undo cos on the right here, I'm going to do inverse cos, which by the way, I might check my mode. Okay, good. So I'm going to do second cos. So this would be -5.5 divided by 9. And that's where this 127 number is coming from. Now, that undoes the cos here. These are gone. So then you have this 0.986 number from this times x, so then you just divide. So I'm going to take this 127 number, divide him by this 0.986 number, and that's where we get x to be 129.44 days, which makes sense with my approximation of maybe about a day 120. I mean, it's hard to tell on that scale. And that's how you could solve for x by using the degree feature in your calculator. Now, technically, once you get to this step, guys, you could do your work in radians. Now, I say that because maybe you are more comfortable doing that, considering this is kind of a weird degree measure. It's not even 1 degree. So, just to show you, if I go to my calculator, go into mode, let me change this to radian mode. So, let's say I am at, let me change my pen. Let's say I'm at this step in my work. I've got -5.5 divided by 9 equals cosine of 2 pi over 365 x. I still have to undo cosine by doing inverse cos. So I'm going to write that on both sides so you guys know what I'm doing. But now I'm doing it in terms of radians. So second cos, I got -5.5 divided by 9. And that's giving me a 2.228 number. Dot, dot, dot. And now you'll have 2 pi over 365 times x. So rather than dividing, I'm going to multiply by the reciprocal. So 365 divided by 2 pi. Whatever I do to one side, I do to the other. Okay, so the whole point of this is on the right-hand side, the 365 and the 2 pi would drop out and you'd be left with x. So in my calculator, I'm taking this number and just multiplying by 365 over 2 pi. So let's see what happens. Oops, I want to do this. This number times alpha y equals, oops, sorry. Let me start again. So I'm taking this number, multiplying by 365 over 2 pi. And I'm doing this deliberately so that I know I'm dividing by both the 2 and the pi. It's that or I had to use parentheses in the denominator. And oh, look at that. It's exactly the same number that I got up above. It's still that 129 number. Okay, so the point of this, friends, is to recognize that you either have to convert this right here to degrees if your calculator is in degree mode to solve this. Or if you don't want to bother with converting, recognize that this is a radian, so change your calculator to radian mode. And then you can do pretty much the same stuff that I did on the left, but with my calculator in the mode so that I read that appropriate language. No matter what, you're going to get the right answer. So ultimately, it's up to you what you want to do. Convert to degrees and keep your calculator in degree mode. Change your calculator to radian and then solve in radian mode. Up to you. No matter what, you're going to get 129 days. All right. Spend a lot of time on that portion because that's the hardest part of this. Now, the scientists who reported this data now inform us that their instruments were incorrectly calibrated. Each measurement for the daylight hours is 15 minutes too long. Adjust your function to part D to account for this change in data. Now, something to keep in mind is that this problem is in terms of hours. So if you're up by 15 minutes, that's 0.25 of an hour. So if everything was 15 minutes too long, that means this midline of 12 is really 15 minutes more than what it should be. So I'm thinking the midline would be more like 11.75, which is why you're seeing this. But then your amplitude will still be the same. So you're just oscillating around a lower midline. And there you go. Next, and I believe last problem to talk through, is this guy about a pendulum. So once in motion, a pendulum's distance varies sinusoidally. So sinusoidally, guys, just means like back and forth. It's just a wave. From 12 feet to 2 feet away from a wall every 12 seconds. Sketch the podium's distance d from the wall over 1 minute interval as a function of time t. Assume t equals 0 corresponds to a time when the pendulum was at its furthest point from the wall. All right, so once in motion, the pendulum's distance varies sinusoidally from 12 feet to 2 feet away from a wall. So we're going to start with its furthest away, so its maximum, which would be at 12 feet. So that's why you guys are seeing this right here. Okay, now between 12 and 2, if I take the average of those, that's 7. That's your midline. And that's why you're seeing this. Let me throw a little label here. Y equals 7 horizontal line being graphed. Now, it says that this happens every 12 seconds. So we go from 12 feet to 2 feet every 12 seconds. So 12 feet to 2 feet, that's what this is here, and that's happening over the course of 12 seconds. So keep in mind, that's actually half of the period here. So from 12 to 2, that's 12 seconds, which means if we go another half of the period, that would make one full period, and then we're back at the beginning. So what you guys are seeing is that one full period of this curve is 24 units. So obviously this is already sketched for you, I'm just explaining it, but you're beginning here, this would be your minimum, and then you're ending here halfway, so halfway between 0 and 12 would be at 6, you're on the midline, and then your other place would be at 6 units from 12, so that would be at 18, you're on the midline again, and that's your one full curve. And then you repeat that for a total of 1 minute. So maximum, okay, go another 24 units for the period. So that's why at 48 you're seeing this maximum. Halfway, you're at the minimum, so we're going down. And then halfway. And then lastly, for 60 seconds, so it looks like you're not going to make it a full period. You'll get another half of a period, which would be another 12 seconds you could fit. You're going just down this slope. Okay, and that is the graph. So keep in mind here that your amplitude is the difference between 7 and 12. So it looks like your amplitude is 5. So some good information to have. Same thing here if you want to look about it in the negative direction. The difference between 7 and our minimum is 5 as well. Now you can figure out your amplitude because it's got to be the average, or it's got to be from the maximum minus the midline. You know the maximum is 12, We know the midline is 7 because that was the average, and that's where this 5 is coming from. Okay, great. So putting it all together into a model for us. Write a sinusoidal function for D, the pendulum's distance from the wall, as a function of time since it was furthest from the wall. Now, sinusoidal function, I want to point out, could be sine or cosine. And that's because cosine is the same thing as a sine curve, it's just off by a phase shift of pi over 2. So rather than saying write a sine or cosine curve, they just say sinusoidal because that encompasses both of them. So a cosine curve would be most appropriate because we're starting above the midline being 7. If we were starting on the midline at time t equals 0, I'd say differently. So cosine is the best fit. Now, since we're starting above the midline, that's where an amplitude of 5 is coming from, with a positive. Now, the plus 7 is coming from the midline. That shouldn't be anything crazy. Now, this frequency takes a little bit of work. Now, we know frequency, I'll add this over here, is equal to 2 pi divided by the period. I know it takes 24 seconds for this whole cycle to happen. So if I'm doing 2 pi divided by 24 and I reduce that, that reduces to pi over 12, which is where you're getting it in this equation over here. And this is a perfect sinusoidal function model for our scenario. Now, identify 2 different times to the nearest tenth when the pendulum was 10 feet away from the wall. Hint, write an equation and solve it graphically. Okay, so we're going to solve it graphically and algebraically. So let's first look at the graph. So identify 2 different times when the pendulum was 10 feet away from the wall. So what you're seeing here is an approximation. If we approximately sketch where y equals 10 would be, like little dashed line, you're seeing 2 intersections. One here and one there. So it looks like we're just shy of 4 seconds. So we'll see how that works out in our math. Just shy of 4 seconds would give us an answer of when we will first hit y equals 10. Okay, so just like what we did in the previous example, you're seeing I'm setting my equation from the earlier part equal to 10 because that's 10 feet away from the wall. Now, just like before, I gotta isolate this chunk right here in order to solve for t. I gotta isolate that cosine part. So you're seeing me subtract 7, and that's where the 3 will come from. And then I would divide by 5, which is where the 3/5 is coming from. So 3/5 equals cosine of pi over 2t. So again, I just subtracted 7, divided by 5, isolated the cosine. Now, just like before, it's up to you what you want to do. Understand that this is in radians. So if you want to keep your calculator in degree mode, then you're going to have to convert this to degrees. So, with that being said, if I do 180 degrees divided by 12, that's going to give me 15 degrees, and that's why you're seeing a 15 right here. That's 15 degrees, okay? Now, if I take the inverse cos of both sides, let me change my calculator back to degree mode since I converted this in degrees. Okay, I'm doing inverse cos of 3/5. And that's where this 53 number is coming from. So you have this equal to, keep in mind these undo each other, so that's why you have just 15t here. I'm going to divide that by 15, and I get this 3.54 number, so about, 3.5 seconds, and that makes sense based on our graph. So if I come back up to about where 3.5 is, that's right there, right? Okay, that makes sense. It's just to the left of that 4-second marker. Now, where would this be? So keep in mind that this is cyclic, right? So if the distance from here to here is 3.5 seconds, then working backwards from the other side of the period would have to also be 3.5 seconds. So I know that at 24 seconds, that's the end of the cycle. So if I go back 3.5 seconds, because again, it's cyclic, it's got to be symmetric here. if I do 24 minus that 3.54 number, that's going to give me 20.5 seconds, and those would be the first 2 times that we would hit 10 feet. All right, so obviously this is one of those scenarios where I didn't fill in the notes, but I went through and explained it. So hopefully this is good for you guys to look back on to help explain the notes if you're stuck on where things are coming from. Good luck.